8A, and a state 7 isentropic. I'm sorry, state 8 isentropic. So that's why I left some space here, because there's a 5s state and a 5 actual state. There's a 7s state and a 7 actual state, an 8s and an 8 actual. These S states are where the pumps and the turbine should end up. But the actual states are where it actually ends up. Now, because, again, I'm going to use an equation much like this for pump 2 as well, I'm not going to worry about the 5s state. I'll just cross that one off my table. Because I could write an equation for pump 2 that looks exactly like this. All I need instead, though, is the pressure at pump 4 and the pressure change between pump 5, or pressure 5, the pressure at state 5 and the pressure at state 4. And then I just need to divide by the isentropic pump work, and we'll have the isentropic pump work for pump 2. So let's do that next. Got to find that in my notes. Here we are. Now, I had to interpolate to get the specific volume at state 4, because understand that state 4 is a subcooled state. Now, actually, we're not quite to the point where we can do this yet, because we don't know enough about state 4 in particular. I will need the temperature or the enthalpy of state 4. So let me pause on that for a moment. So we're not done with this pump work yet. We're going to do something similar to what we did for pump 1. We need some more information about state 4. I mean, we've got the pressure change, that's no problem. We've got the efficiency, but I need the specific volume of this subcooled liquid. And I don't have that yet. So let's see, what can we attack? Well, let's see. How about the turbine? Could we do something on the turbine side? We should be able to. We should be able to figure out what the enthalpy at state 7s should be. How would we do that? Well, we know that the entropy in state 6 is something that we can find. In fact, we already have. We've got it right here. So the entropy in state 7s would be the same, because it's an isentropically related state to state 6. Similarly, since this line continues down vertically, 8s would also have the exact same entropy. But in the real world, the 7a and 8a states are going to have higher entropies. But could we find what the enthalpy should be for state 7s? Well, we can. That's really not so bad, because look, for state 6, well, let me back up. For state 7, we know that the pressure in state 7 is 140 psia. We know that the entropy in state 7, this is state 7s by the way, the entropy in state 7s should simply be 1.6812 BTUs per pound mass. Try to make a B and an L at the same time, it didn't work very well, per Rankine. That's 2 pieces of information, and that's all we need to know in order to come up with the enthalpy in state 7s. So let's see how this works. I always recommend that you go and you look in the saturated table first. So go to the pressure table, page 966, look for 140 psia, and then go across to the entropy of saturated vapor. I read 1.5757, but our entropy is higher. What that means is that state 7s is in fact in the superheated region. I actually just kind of got lucky here. I couldn't remember where state 7s ended up. But it does end up in the superheated region. That tells me that state 7a will definitely be in the superheated region. So what that means is that I'll actually have to go over to the superheated tables, and I probably will not find this exact entropy at 140 psia. Let's see if we get lucky. Page 969, 140 psia is the top row, center column, and I'm looking for an entropy of 1.68. I find 1.66 some odd and 1.69. So I would have to interpolate between these two. As a matter of fact, I've already done that, and I came up with an enthalpy for state 7s. Let me write out what I did. This may be beneficial to you. and then other interpolations I'll leave you to follow through the book. 1.6812 less 1.6686 divided by 1.6948 less 1.6686 multiplied by 1301.1, I'm sorry I'm out of space, I've got to break the line, minus 1275.3. Understand that these are all entropies, S, and this difference here, these are enthalpies. Okay, so then finally plus 1275.3, and that of course is an enthalpy as well. All three of these are enthalpy numbers. So these would have units of BTUs per pound mass, and these would have units of BTUs per pound mass per Rankine, but of course they cancel out. So from that, I found the enthalpy in state 7S. If you plug this into your calculator, you'll find what we ought to write on the 7S row. And that comes out to 1287.71. So that's what the entropy should have dropped to coming out of this turbine if the turbine were isentropic. But in reality, what will happen is that the turbine will not extract as much energy from the steam as it should have. It will extract less. And so I expect for state 7A to have a higher enthalpy than 1287. Let's see what happens. Well, the isentropic efficiency, we're pausing on this for a minute. The isentropic efficiency of the turbine is defined as the amount of power that you get out of the actual turbine over the amount of power you get out of the isentropic turbine. You see, the isentropic turbine would produce more power than the actual one does. Actual systems don't perform as well as ideal systems. And one way to write this is by the mass flow rate through the turbine multiplied by the enthalpy change across the turbine. Now we've got to be careful here because there's really two sections to the turbine. There's a drop from state 6 to state 7 and from state 7 to state 8. Not all of the mass that came into state 7 goes into state 8. Some of it comes out, and the majority of it, 8.5 pounds per second, actually continues through. But let me just look at this as the isentropic efficiency of just the first section of the turbine from state 6 to state 7. If I do that, then this would be H6 minus H7A over H6 minus H7S. Okay. Obviously, I can cancel the mass flow rate and just look at the specific work ratio of the actual turbine to the isentropic turbine. And since I know the isentropic turbine efficiency, I know the enthalpy in state 7S, and I know the enthalpy in state 6, I can solve for the enthalpy in state 7A. And that looks like this. H6 less isentropic efficiency of turbine, H6 less H7S. Okay? Now, you know H6, it's right here. You know H7S, it's right here. You know the isentropic efficiency, it's 86%. So you can calculate H7A. When you do that, it comes out to about 1319.1. And you see that these numbers came out exactly as I predicted. The actual enthalpy coming out of the turbine at state 7 is more than it should be. The turbine has not extracted as much energy from the fluid as we would like. Okay, well that takes care of state 7 actual and 7 isentropic. Well, we could do the same thing for state 8, couldn't we? For state 8, what do we know? Well, let's see. For state 8, we know the pressure, and for state 8S, we know what the entropy should be. So P8 known, S8, and I should say S, is known. Right? Now notice I didn't say P8S. Why not? Well, just like with state 7, I may have written P7S, but I didn't mean to do that. The pressure is the same no matter what. The pressure coming out of state 7 has to be 140 psia. So we've got to do whatever we can to make that the case. That's why this is just one pressure line for 140 psia. Similarly, the condenser pressure, which was what, 2 psia? The condenser pressure is the same regardless of whether it's state 8A or state 8S. Now, I imagine that 8S is going to end up in the saturation region, but let's find out. Let's go to a pressure of 2 psia in the saturated tables. I just passed it. So page 966 again. At a pressure of 2 psia, the entropy of saturated vapor is 1.9194. The entropy we have for state S is 1.6812, significantly less than 1.9194. That means me putting this point inside of the vapor dome is correct. There would be a quality, in other words, a fraction that is in the liquid phase in state 8S. And so I should first of all begin by calculating the quality, or in other words, simply the percentage that's still in the vapor phase. So this would be S8 less SF over SFG. So let's see, what the entropy should be is 1.6812. If you look up SF at 2 psia, I haven't yet, or I haven't mentioned on camera, it's 1.7499. SFG is 1.74444. And so we can calculate the quality in state 8S as about 0.8634. This allows us then to calculate the enthalpy in state 8S as HF, understand I'm doing this all at 2 psia, HF, let's see, minus X8S HFG, also at 2 psia. I'll write in the numbers so you can follow. This HF would be 94.02. We've actually seen that number before. That's the same saturated enthalpy as state 1, because it's just at 2 psia. Let's see, plus 0.8634, the quality, you see, multiplied by HFG, which is 1021.7. And I'm using all BTUs per pound mass, so I haven't written down my units. But when you do all of this, when you plug all this into your calculator, you'll find that the enthalpy in state 8S is, let's see, 976.19 BTUs per pound mass. Okay, but that's state 8S. I want the actual state. How do I come up with the enthalpy H8A? Well, again, these states are related by the isentropic efficiency of the turbine from state 6. And so the isentropic efficiency of the turbine would be H6 minus H8A over H6 minus H8S. Now you might look at this and say, well, wait a second. Some of the mass goes the other way. Are you sure that this is correct? It is correct, and you can prove this to yourself by noting that this is the same thing as, let's see, it would be the enthalpy drop from state 7A to 8A over 7S to 8S. Check and see that this makes sense, but this should work also. This would be state 7A less state 8A over H7S less H8S. Plug that into your calculator, pause the video and try it, but you should get the exact same thing that we end up with here. Notice that you've already got these, you've got 7A, 7S, you've got H8S. Similarly, we have H6 and H8S. And so the only unknown, since the isentropic efficiency is given, the only unknown is state H8A. So to calculate, I guess we can do it up here, H8 actual, the enthalpy in state 8 actual, for that it would be, I'm going to use this first form. You can try this. Let's see if it works. It should. H8A is equal to H6 minus the isentropic efficiency times H6 minus H8S. Okay, notice we've got H6, isentropic efficiency, and H8S. And so once you plug in all the numbers for H8A, you come up with, or at least I came up with, an enthalpy of 1051.23 BTUs per pound mass. Okay, now I don't really care what the entropy actually is here. I could look it up, I could figure it out, I'd probably have to interpolate it. I don't care, I've got the enthalpies and that's what I really came for. Okay. We're still left with a few questions. In particular, let's see, we know everything that we need for state 3. I don't really care about the temperature of state 3, I don't believe. Well, it's going to be the same as the temperature of state 7. We may as well look that up. It's a, actually no it won't, because 7 is slightly superheated. I'd have to interpolate to get at the temperature at state 7. I'm not going to mess with that because it won't really help me in the questions that were asked. Why did I write that the net power output was 0? I think I meant to put a question mark there. I apologize. In fact, what all were we supposed to find? Oh, there we are. We were supposed to find the heat transfer rate into the boiler, Q dot N, and the net power output. So, sorry, I left that as a 0 for a long time. I didn't mean that. Hope I haven't confused you to this point. So let's see, where was I? Oh, there's a few states we still have to find, and I was curious what the temperature is at state 3, and that's something easy to figure out. All I really have to do is realize that state 3 is a saturated state at 140 pSIA. Look up 140 pSIA and write down the temperature. So that's 353.03 degrees Fahrenheit. Now that's a great temperature for baking bread or baking anything really. Normally you turn on an electronic oven for baking in your home, it'll be set by default to 350 degrees Fahrenheit. So this is ideal baking temperature. I guess that's what this process plant does. It says it's a food processing plant. So it's baking bread or something. Okay, so somehow I have to deal with state 4 and state 5 actual. Those are the two that remain where I need information because those are the two that are missing enthalpies. Now to deal with this, what we have to do is first of all realize that state 4 is the key defining state 5, right? Because state 4 is what we need in order to define the specific volume, and then state 5 will drop out of the specific pump work if we want it to. So how do we get at what's going on in state 4? Well, this is a mixing chamber that is mixing state 3 and state 2, but we know the enthalpy in state 3 and state 2. If we just knew the flow rates, we could write an energy balance. Oh, wait a second, we do, don't we? We know the mass flow rates, those were given. So let's write an energy balance around that mixing chamber. So this mixing chamber right here, you copy it. State 3 comes in, state 2 comes in, and state 4 leaves. Now, if I were to write an energy balance around this, I would like to write it in terms of mass fractions because y percent goes this way and 1 minus y percent comes in this way for 100% output. If I were to write this in terms of an energy balance, what I would write is that 1 minus y times the mass flow rate through the boiler, let's just call that m.6, multiplied by the enthalpy carried in stream 2. Understand this quantifies the amount of the rate at which energy is carried by mass in stream 2, plus y, this fraction, of the mass flow rate through the boiler, times the enthalpy in state 3, that quantifies the energy carried in by the condensate in state 3. This is equal to the mass flow rate in state 6, 100% in other words, times the enthalpy in state 4. And again, what happens is the mass flow rate in state 6 cancels out. And since we know the mass fraction, well, do we? Sure. The mass fraction y is simply 1.5 divided by 10. Why is it that? Because 1.5 pounds mass per second goes this way. Why wouldn't we divide that by the 8.5 that goes this way? It's because the reference for this mass fraction is always the flow through the boiler, which is the total flow. So this will come out simply to 0.15. So the mass fraction 0.15 is known, and solving for the enthalpy in state 4, that's already done, right? So the enthalpy in state 4 would be equal to, let's see, 1 minus y would be 0.85 times H2 plus 15% of H3. Now we've got H2 and H3, and so finding the enthalpy in state 4 is just a matter of punching buttons on a calculator. It comes out to 129.06 BTUs per pound mass. Now, we still want to find the specific volume at state 4. But all we have is the enthalpy at state 4. But I claim that the state is solved because look, we've got the pressure and the temperature for state 4. So what we're going to do is calculate the specific volume of saturated liquid at, well, rather than doing it at a temperature, which we don't know, I'd have to interpolate. Well, I would interpolate to get the temperature at state 4. Why bother? I've already got a number that represents the state. So I should interpolate this at HF, you see, at H4. Assuming that this is the enthalpy of saturated liquid. Now obviously state 4 is actually in the subcooled region, but all I'm doing is I'm approximating it as if it's on the saturated liquid line. This is equivalent to taking the enthalpy or the specific volume to be the enthalpy or specific volume on the saturation line given the temperature. Okay, so it's the same thing. So let me write this out so you can see what I'm doing. Let's just write it that way. Let's see. Let's do it this way actually. HF is being approximated as H4. And so what I got was this. Let's see. I'm going to move down just a little bit. 129.06 less 120.90. Understand these are enthalpies I'm writing in. Of course, all of these come from the steam tables. This is the actual enthalpy at that state, assuming that it is an HF. We're pretending that it's an HF. Times the specific volume difference between the two data points I actually have in the table, 0.01641 less 0.01636 plus 0.01636. Now understand that these are all specific volumes, and of course they all have units of cubic feet per pound mass. So when you finally plug all this in, you find that this is about 0.01640 cubic feet per pound mass. So now we have the specific volume that we can plug in to find the pump work and state 2 actual. Okay, so specific volume 0.0164 cubic foot per pound mass. Of course, the pressure change between state 5 and state 4 is 800 versus 140. So 800 less 140 PSIA. I used a conversion factor before. Understand I would have to use it again to go from PSIA cubic foot to BTUs, but I will just show you the result. Oh, let me not forget to divide by the isentropic efficiency of the pump. Okay. But anyway, you end up with a pump work of about 2.329 BTUs per pound mass once all the conversions are done. Now, in order to calculate the enthalpy in state 2A, understand that this pump work is H2A less H1. And I'm sorry, I switched back to 2. I'm dealing with the second pump. So this will be H5A less H4. So if the only unknown now is H5A, I know H4, I know the specific pump work, and I shouldn't say 2A. Well, I meant pump 2 actual. Maybe I should have used II actual. So this would be pump 1, and this would be pump 2, the way it's clear. I didn't intend to confuse with state 2 actual. My apologies if I did. But anyway, since the only unknown is H5A in this equation, now I can solve for it. I can calculate it. And that comes out to 131.39 or so BTUs per pound mass. Well, why did we do all of this? Well, the way to solve a cycle problem is always to go around the entire cycle, solving for each and every state, given process knowledge, understanding how the turbines work, understanding how the pumps work, understanding that condensers have saturated liquid coming out of them, same thing with the process heater, understanding the boilers where all of the mass flows through. And the purpose of all of this is that once you go to answer the questions that were actually posed, you'll find you need all the enthalpies. Well, most of the time. So one thing you might want to do, especially on exams, is write out equations for what's asked for. That way, if there is an enthalpy that you don't need, you don't have to find it then, see? And that can save you some time. So I probably should have started with that. For example, Q dot N would be the mass flow rate through state 6 times the enthalpy change across the boiler. And that's pretty easy, right? So that would be H6 less H5. So I certainly need H6 and H5, and I'm going to need the real state 5 actual, right? I've got all those numbers, so I can actually plug in and find the heat flow rate in. Well, H6, that's 1512.2. H5 actual is 131.39. These are both BTUs per pound mass. And so the actual heat flow rate into this process is about 13,308.1 BTUs per second. That's one of the questions they had. So it's a good thing that I found H5A and H6. Now sometimes, in order to find these, you have to go through other parts of the problem. Notice, to find 5A, I had to deal with the pump work, which meant I need state 4, which meant I need states 2 and 3, which meant I had to deal with the pump work and an energy balance and the process heater. So ultimately, I had to solve the whole thing anyway. Most of the way at the time, that's the way this turns out. So just from looking at these and realizing what I had to do just to get 5A, you realize I had to solve the whole diagram. That's, as I said, not always the case. How about the net work output? The net work output can be arrived at a couple of different ways. In my case, here's what I did. I said, well, let's see. There's mass flow through, and you know what? It looks like I may have made a mistake. Hang on just a second. So 7, 8, 6, 7. Yes, I've made a mistake here. I have made a mistake. I have just calculated the power output of the turbine. Let me show you what I've done. I'll grab a calculator in a moment and we'll fix this. Here's what I did. I said the mass flow rate in state 6 times the drop in the turbine initially. All of the mass drops from state 6 to state 7, producing power. But only 1 minus y% of that drops, of that mass flow drops from state 7 to state 8. I just realized I'm going to have to fix my solution here. And so then I went ahead and plugged in numbers and said, well, let's see, this is 10 pounds mass per second. We could, of course, factor it out, right? So let's do that. H6 minus H7. I'm just going to write it in because it would take up too much space. But you've got state, and notice I'm using state 7A, right? We don't care about state 7S anymore. We don't really care about state 8S anymore for the same reason. We want the actual numbers, right? Plus, let's see, 1 minus y multiplied by H7A less H8A. Okay, so you've got all of these numbers. Y, of course, is still 15%, 0.15, and you've got the enthalpies from the chart over there. So I got 2,332.8 BTUs per second, but that's just the power output from the turbine. The pumps require work. So at this point, probably the easiest thing to do is just subtract off the pump work. So the net power output would be the power output from the turbine less the work consumed by pump 1, less the work or the power consumed by pump 2. Now, this first term is no big deal, so we'll just leave it alone. But the power required for pump 2 would be the specific work, I'm sorry, for pump 1 would be the specific work for pump 1, which we had a moment ago. I've still got it on my sheet. multiplied by the mass flow rate through pump 1. But that would be the mass flow rate through state 6, but not all of it, right? Because only 1 minus y flows through that pump. And then for the second term, minus, let's see, I guess I will leave it here so it makes sense. So for pump 2, it would be the specific work for pump 2, which I still happen to have on the board. That's right here, this 2.329 BTUs per